Good morning, everybody. So we'll start our day 3, which is like we take out from the radio and go to the optical. So we have a lot of new things to learn today. And Kritti and Sunil are here to kind of take us through the optical study of FRB, its host galaxy, all those things. So we'll start with the first some of the overview lectures today, and then we'll go to the hands-on session. And you have received, I think, the Slack message from Yash about the Dockers and other things. So hopefully you have done that, because there's like 20 GBs of data file you have to get download through. So if you haven't done that, then maybe you can just put it into the download while the talk is happening, so that you'll be well prepared after the coffee break when you start the hands-on sessions. Okay.
All right. Hello, everyone. My name is Kritti Sharma. I'm a graduate student at Caltech. And today, both me and Sunil will be coordinating the sessions, and we are beginning with a bunch of overview talks of what we can achieve with optical studies of FRB host galaxies. I'm pretty sure everyone in the room is already aware of what FRBs are, but here's the ritual where I just introduce what FRBs are as usual. So the first FRB, also called the Lorimer burst, was discovered in archival data from Parkes radio telescope, where they were looking at Magellanic clouds, particularly looking for pulsars, but they ended up finding this bright 30 Jansky burst with a duration of about 5 milliseconds. And what really caught their eye was that the dispersion measure of this particular burst was 375 parsecs per centimeter cubed, which clearly exceeded our expectations from that of Milky Way, which is like less than about 100 parsecs per cc. So that kind of established that it might have an extragalactic origin. The localization uncertainty for this particular burst was about 10 arc minutes across, so it was difficult for us to pinpoint where exactly it was coming from. But moving forward, the community has been building up larger FRB samples, and all of them seem to be quite bright about Jansky flux densities. They are quite brief, about less than millisecond durations. Majority of the population seems to be apparently non-repeating. They don't have a lot of repeat bursts, or maybe we're missing them out. They have extragalactic origins, again established by their dispersion measures and later by host galaxy spectroscopic redshifts. And they're actually also quite frequent. The all-sky rate is about 10 power 5 per sky per year, which is quite huge. The reality of these bursts was actually established by Thornton et al. In 2013, where they looked again at higher galactic latitudes looking for FRBs. And again, they found a bunch of bursts which didn't seem to have a terrestrial origin. So that established that FRBs are indeed real. The key question that we are interested in is what are FRB sources and where are they coming from? And one of the questions that we want to answer is, where do the FRB sources sit in this landscape of stellar progenitors? So from left to right, it's increasing stellar progenitor age. So on the left, we have very young, massive, stripped, enveloped stars like that of O-type stars, which lead to long-duration GRBs or superluminous supernovae. Next, we have massive single stars, which form neutron stars or black holes in core collapse supernovae. Moving forward on timescales of a couple of 100 mega years, we have binary neutron star mergers or binary black hole mergers, which are known to lead to, for example, short duration GRBs. And finally, on the oldest end, going all the way up to giga years, we have degenerate white dwarf systems, which could lead to type 1a supernovae or calcium-rich transients. So we would like to understand where FRBs sit on this wide range of stellar progenitor ages for transients. Just to set the ground, what do we really learn from host galaxy studies? So since most of these FRBs are at large extragalactic distances, it's difficult for us to pinpoint what exactly the source is. So we have to rely on indirect proxies of what their sources might be. And good examples of the same actually come from different transient classes. So the plot on the left here is showing cumulative density function of the stellar mass of host galaxies for different transient classes. The curve in pink here is for superluminous supernovae, and the one in orange is for long duration GRBs. And you can see that it's clearly offsetted from core collapse supernovae, which is shown here in green. So that allowed astronomers to establish that superluminous supernovae and long-duration GRBs occur in relatively lower mass galaxies. And since mass metallicity correlation is actually in positive direction, that implies that there may be a preference for lower metallicity. And if you think about it, it actually makes sense because in case of low metallicity, you have low wind-driven mass loss rates, and that allows your star to retain its actual mass and form a black hole progenitor at the end of its life. Another example of the same is that of galactocentric offset distribution of transients. So for example, the curve in red here is for long duration GRBs, and the curve in blue here is for short duration GRBs. So you can see that for short duration GRBs, there's a preference for a systematically larger galactocentric offsets. And that helped us establish that there could be a preference for delayed formation channels or channels that involve mergers and kicks in their formation channels. So given all this, we went ahead and tried to localize the first couple of repeating bursts with VLBI. And one of the first bursts that was ever localized is FRB 121102, which was localized to a dwarf star-forming galaxy. So here, this tiny cross, which I'm not sure is clearly visible, is the location of the FRB. And the image that you're looking at here is in UV. So you can see that it's clearly associated with the small star-forming region in its host galaxy. In optical data, we also found a compact persistent radio source about less than a parsec in size. And it also had a high radioluminosity. So all of this storyline was actually quite consistent with a young formation channel like that of core collapse supernovae. Next, FRB 180916b was localized to this Milky Way type spiral galaxy, which was quite massive, about 10 × 10 M suns. And it also had a star formation rate comparable to that of Milky Way, which is 1 per solar mass per year. The location of the burst, which was in this region, was at an offset of about 250 parsecs from the nearest star-forming region. And there was some turmoil in the community whether or not this offset is actually consistent with the magnetic field decay timescales. So is it possible for the magnetar progenitor to travel from its birth site in the star-forming region to its current location where the FRB occurred, given this offset? So there was some discussion that it's possible that it involved some sort of a binary formation channel, but it wasn't very super clear at the time. The third FRB 2020-0120E, which I think was completely mind-blowing, it was associated with a globular cluster of M81 in our neighborhood. So if you compare it with the previous two localizations, it's a very different environment because in case of globular clusters, you don't expect them to have a lot of young stellar population. It's mostly old stellar population. So it hinted towards something that is not really a young magnetar origin. Maybe it's a binary neutron star merger. Maybe it's an accretion-induced collapse event or white dwarf. Who knows? So this really requires us to continue building larger samples of FRBs to understand what the dominant formation channel of these sources could be. One of the dream scenarios for anybody working on understanding what FRB sources are came true back in the day when an FRB-like burst was detected from a magnetar in our own galaxy. So CHIME and STARE-2, both of them detected an FRB-like weak burst, which was temporally coincident with that of an X-ray burst from Conus Wind from this SGR 1935 magnetar. And based on this coincidence, they established that the rate of such radio bursts from magnetars that can have such X-ray flares should be about 1 per 25 years. And further follow-up in optical and radio helped us found a supernova remnant at the location of the magnetar. So here, the blue point here is from X-ray observation. So that's the actual magnetar. And the red halo that you see here is the supernova remnant itself. Further, by measuring the proper motions of this magnetar and extending it down by the age of this particular supernova remnant, we found that it's actually coincident with the centroid of the supernova remnant, which implied that this particular magnetar must have formed by the specific remnant, and it's actually associated with the same. So far, we all have been working together towards this bigger goal of building larger samples of FRB host galaxies. And several instruments have been playing a key role in here, including MEAR-TRAP, CHIME outriggers, ASCAP, and DSA. I must highlight that most of these FRB host galaxies that we are seeing here are for non-repeating bursts. So that's the key achievement in here, that we were able to do arc-second scale localizations for FRBs without them having to repeat, which is the biggest achievement here. All these host galaxy cutouts are arranged in increasing order of their redshifts, and they go all the way from redshift of 0.01, which is like 50 megaparsecs, to redshift of 1 to 2 recently by Meerkat. Once we identify such an FRB host galaxy, the next step is to follow it up, do imaging, and obtain the spectroscopy to understand the host galaxy and therefore the FRB sources better. So we dig up archival imaging and spectroscopy data from various surveys like PAN-STARRS, SDSS, WISE, etc. So here as an example, I'm showing one of the bursts from DSA 110 team, which originated from this particular host galaxy shown in marked as red, and the cyan region is the 90% localization region of this burst. We obtained its optical spectroscopy with Keck, where we placed the slit along this green line that you're seeing here and obtained this particular spectrum. And this is honestly one of the best spectrum I've seen in my life, because most of the FRBs end up being so far that the spectra are really trashy. So this is one of the cleanest spectrum that you would ever see. You can clearly spot these emission line features like O2, H beta, and O3, which are star formation indicators. And this one is also actually quite pretty because it has these stellar continuum absorption lines, which are characteristic of old stellar population ages. So once you have imaging and spectroscopy of the host galaxy, what do you do next? We try to model the galaxy stellar population environment. And for doing that, we leverage several established results like that of mass metallicity, like that of mass luminosity correlation. A brighter galaxy is expected to have a larger mass, is the simple correlation that I'm talking about. And one of the old results from back in, I think 2001 is from Bell and De Jong, where they looked at correlations of mass to light ratio with that of their optical colors. So using that, you can actually do the K correction and actually measure the host galaxy stellar mass as well. And these are actually important because they help us break the very important age metallicity and dust degeneracy when doing the actual stellar population modeling. Apart from that, the spectra of the galaxy are actually again very important. So here I'm showing the evolution of luminosity for a particular galaxy as it ages from 4 mega years all the way down to 10 giga years. So you can see that a very young star-forming galaxy has these bright emission line features. And as the galaxy ages, you start to seeing these absorption line features from stars or the stellar component of the galaxy. So combining the information from mass luminosity correlations as well as emission and absorption line features, you should be able to comment something about the star formation rate of the galaxy and the age of the characteristic stellar population in the galaxy. Specifically, we use software called Prospector, which you're going to learn more about later in the day-to-day, where we'll do the actual galaxy stellar population modeling. Here, we combine photometry, which are all the points right here in blue, and spectra, which you probably can't see clearly, but here you can see the data in blue is the observed spectroscopy. So we try to jointly model the observed photometry as well as spectroscopy by leveraging all these correlations that I already mentioned of, where nebular emission lines are actually probing young stellar population, the absorption line features are probing old stellar population, the luminosity probes your stellar mass, and the infrared emission is basically just your UV emission, which is reprocessed by dust. So all of these correlations are actually being built into the software called Prospector, which we use to infer all these galaxy stellar population properties. After conducting such an analysis, you'll have basic properties of the galaxies like SFRs and stellar mass, metallicity, etc. measured. So where do we go from there? One of the first things that you could do is compare your FRBs with that of background galaxy population. So the plot here is showing star formation rate versus stellar mass in 3 different redshift bins for background population of the galaxy shown here in the background as these shaded regions. So you can see that as you go to higher redshifts, there's like a drift in the star forming main sequence of the galaxies. All the points here are the FRB host galaxies that have been published to date. So, for example, the circles are from ASCAP, the stars are from DSA 110, and a few of the squares are from CHIME. So you can visually see that FRB host galaxies are consistent with the background galaxy star forming main sequence. So that tells you that there could be a preference for star formation rate. There are, again, a handful of host galaxies which don't have a very high star formation rate. They tend to be quiescent, but there's no clear correlation with the galaxy offset measurements. So it's difficult for us to comment on whether or not there's a preference for delayed formation channel for these specific FRBs. Furthermore, the colors here for all these points are specific star formation rate multiplied by the Hubble time at the redshift of the FRB. So you can think of it as an indicator of the degree of star formation. So the blue ones are the ones which are highly star forming, and the red ones are quiescent ones. So again, you can see that majority of them seem to be star forming in nature. From such an analysis, you can try to quantify whether or not we trace star formation or whether or not there's deviation from star formation. So the plot on the left, for example, is showing the dispersion measure versus R-band magnitude of galaxies. So dispersion measures are expected to have a nearly one-to-one mapping with redshifts. So all these points in the background, these tiny ones, are known core collapse supernovae. And the squares or the stars are the ones which are FRBs. So you can see that while core collapse supernovae expand all the way out to these 0.01 L star galaxies, there seemed to be a deficit of FRBs in such galaxies. And using such by quantifying the statistical significance of such a deficit, which was about 3.2 sigma, we went ahead and thought more about what could have actually caused this deficit. And if you indeed look at stellar mass distribution of FRB host galaxies, which is in blue, core collapse supernovae, which are here in green, and compare it with background galaxy population weighted by SFR, which is the curve in red, you can see that core collapse supernova almost perfectly trace star formation. But for FRBs, there seems to be an apparently 3 sigma deficit of this. And if you indeed fold in a metallicity dependence, where you say that FRBs are more likely to occur in higher metallicity galaxies, then you can try to recover your original distribution much better. Of course, the uncertainties on FRB host distribution is quite huge because of Poisson uncertainties. The sample size is small, but this is something that we can continue to monitor going forward to understand whether or not there could indeed be a metallicity dependence for FRB source formation channels. There have been other methods to account for this low mass deficit. For example, in this recent work by Nick Lourdes and Horowitz, they tried to look at combinations of stellar mass and star formation rate that could indeed recover this stellar mass distribution of galaxies. And they argue that it's possible that there's a tiny fraction of FRB hosts that could be tracing stellar mass instead of star formation rate, similar to that of type 1a. So there could be a combination of multiple formation channels. Where are we trying to go with all of this? As we are trying to answer what's the broader question of this magnetar formation. How are FRB progenitors most likely magnetars being formed? We know that about 85% of massive stars, at least in Milky Way, exist in binaries, which kind of makes sense. These massive stars are formed in huge clouds where you expect to find multiple stars at the same time. So the massive stars are probably born with companions. And we also know that metal-rich stars are relatively larger in size. So if they exist in binaries, they are more likely to undergo unstable mass transfer and lead to mergers. So why are mergers important? This is because a single massive star is not expected to have huge magnetic fields to form magnetar at the end of its life. So this is one of the unsolved problems in the field of magnetars themselves. As an example, the plot on the left is showing the evolution of one of the blue straggler stars, which existed in an area full of stars which were relatively older, which made us wonder why it could be that young. So the argument made by authors there was that it must have undergone a stellar merger to form a magnetic massive star. So it's unstable, it spins up rapidly and sheds off some of the mass to form a magnetic massive star with about 5 solar radii in size and about 10 kilogauss in terms of magnetic field. And then after evolution along its main sequence star, it could form a compact object with strong enough magnetic fields. So it could be a black hole, or it could be a magnetic neutron star or a magnetar. Independent evidence for the exact same comes from a search for ejected or binary companions for magnetars in our own galaxy, where in search conducted by Miles Sherman, we were looking for companions of magnetars in Milky Way, and we didn't find any good candidates. So given the fact that about 85% of massive stars were born in binaries, the fact that majority of them end up being isolated implies that at least 78 to 80% of them must have undergone a binary merger before the core collapse supernova occurred. All of this makes sense, but given there's this open question of multiple formation channels. So if you look at stellar mass distribution of FRB host galaxies and compare it with different classes of transients, what you'll find is that you can't really rule out similarities with type 1a supernovae or short duration GRBs, even at 3 sigma level. So that might imply that there could be other formation channels like that of NSBH mergers, AICs of white dwarfs, BNS mergers, or binary white dwarf mergers. And really, the problem here is constrained by the rates. We don't fully understand what's the rate of AICs of white dwarfs or binary neutron star mergers very well, because BNS mergers would have jetted emission, and AICs of white dwarfs are just simply difficult to detect because their optical signatures are at least 5 magnitude fainter than that of typical supernovae. We looked at the radio light curves for BNS mergers as well as AICs or white dwarfs, and what we found is that such transients are better looked at radio instead of in optical. And what we found is that their radio emission, even at gigahertz, is expected to be really luminous. So you can try to look for these transient classes in radio data instead of optical. And we looked at them in the VLS Sky survey data. And we found a couple of transients using which we had put rate constraints on AICs, which form pulsar wind nebulae, or AICs involving dense CSM interaction, and short duration GRBs or BNS mergers. And the rates for all of them is like 10 to order of 100 per gigaparsec cube per year, which is much smaller than that of FRB rate, which is like orders of magnitude larger. So that mostly implies that it's unlikely that any of these is the dominant formation channel for FRBs at the point. Another way of looking at FRBs could be through high resolution imaging of their host galaxy environments. So in works led by Alex Mannings and Michelle Woodland, they compiled a sample of deep UV and IR HST imaging of host galaxies together with Gemini adaptive optics aided observations of these host galaxies. And using such high resolution imaging of the host galaxies, they tried to compile the normalized host offset distribution for these FRB sources. And they could rule out similarities with that of calcium-rich transients and long-duration GRBs with a very high significance. So but still this data supports a diverse young to intermediate age formation channels for FRBs. More recently, in work led by Alexa Gordon, they looked at the profiles of FRB host galaxies to try and understand whether or not there's a preference for coincidence with spiral arm features in their host galaxies. And what they found is that even though about 85% of galaxies in their sample were spiral galaxies, only 20 to 46% of the FRBs seem to have favored the coincidence with that of spiral arms. And furthermore, comparing it with that of globular cluster formation channel, what they found is that only about 10% of the FRBs seem to have a preference for old stellar population or globular cluster formation channels. And overall, what they found was that most of these FRBs trace these smooth stellar light distributions, and there's no clear preference for coincidence with these active star-forming regions in the host galaxies. So far, FRB community has been building up on larger and larger samples of the FRB host star formation histories, which is basically an account of SFR as a function of look back time for their respective galaxies. And we have built a sample of about, I think, 50 FRBs for which we have these detailed star formation histories measured. So given this data, is there something we can learn about the age of the stellar progenitor or how old the FRB source itself might be? And one of the characteristic ways this has been done in the past for different transients is through the delay time distribution, which is mathematically just a convolution of delay time distribution with that of the star formation history of the galaxy, which gives you the rate of the transient in a particular galaxy. So as an example, the plot on the left shows the delay time distribution for core collapse supernovae. So in simulations, folks have found that for single progenitor formation channel, at least for core collapse supernovae, the upper limit on age is about 50 mega years, which is largely limited by the nuclear fuel burning time scale. But there seems to be this tail in the formation channels for core collapse supernovae, which is largely coming from binary evolution scenarios and extends all the way out to 250 mega years. Observationally, for short duration GRBs, in this work led by Michael Zebin, they compiled exponential star formation histories of about, I think, 80-ish short duration GRB host galaxies and tried fitting it with a power law delay time distribution model. So with that, they were able to establish a minimum delay time of about 100 mega years for SGRBs and a power law slope of about -2, which is consistent with the theoretical models as well. Similar studies for type 1a supernovae have also been conducted with exponential star formation histories and power law delay time distribution models. So with FRBs, given their optical host galaxy information, we can try and fit for the FRB delay time distribution as well. And we have put in some initial efforts into trying to do repeat the exact same exercise for FRBs with different models, including power law, double power law, or a broken power law, and even a combination of like Gaussian and power law, which could be a combination of young and old stellar population models. But at the moment, we only have like order 50 FRB host galaxies with star formation histories measured, which is not sufficient for us to be able to statistically distinguish between all of these models. But there are also some technical challenges with using this method altogether, because if you're using the global star formation history, then it's tracing the characteristic stellar population age, which may not really be representative of the local environment of the FRB source itself. And a good example of this is the FRB, which was associated with M81. So the local environment has preference for old stellar populations like that of globular clusters, but the galaxy itself, M81, is fairly star forming. So you really need local information of the FRB host galaxies to be able to comment on the typical characteristic progenitor age. Several of us have ongoing programs to actually look at the local FRB source environment for FRBs at low redshifts. So for example, here I'm showing H-alpha map of an FRB host galaxy called Mark. So this region here marks the 90% localization region of this FRB. And it's coincident with the star forming region or H-alpha region in its host galaxy, which again establishes a progenitor age of less than at least 20 mega years. And similarly for FRB Mizu, which you'll hear a lot about in the rest of the day today, it's also coincident with fairly active star forming region in its host galaxy. So using such resolved spectroscopic studies, at least that trace the H-alpha luminosity comparable to that of Milky Way star formation surface density, you can comment on what's the limit on the progenitor age. So currently, FRB community has several ongoing efforts in this direction. Lastly, I wanted to highlight that we have come a long way. The first FRB had 10 arc minutes of localization uncertainty. From there, we went to milliarc-second precision localizations of FRBs on account of their repetition. From there, we went to about arc-second scale localizations for almost all FRBs, including non-repeaters. And now Chime outriggers is pushing further into VLBI mass localizations for all non-repeaters together. And they established the accuracy of their methods more recently by this FRB, which is the brightest known FRB to date, which was localized at a large offsets from this spiral host galaxy, again in our neighborhood, at about, I think, 40 megaparsecs. If you zoom in at the location in NIR, it's actually it has these multiple blobs in NIR, which are consistent with being RGB clumps or main sequence stars, but not a magnetar or a pulsar wind nebula. And furthermore, looking at it with KCWI, which is an IFU spectrograph, we found that this FRB location is at an offset of about 200 parsecs from the nearest star forming region. So really with such VLBI millisecond localizations, we are pushing in the direction of looking at FRB sources in a zoomed in fashion and to really resolve what the actual FRB source might be. Lastly, I want to highlight that understanding FRB host population and their progenitors is not important just for understanding what FRB sources themselves are. It's also important for all the cosmological applications with FRBs. Because if you write the FRB dispersion measure, it's a sum of the host contribution with DM cosmic, which is what we are interested in, plus Milky Way contribution. So this host contribution is degenerate with the quantities of interest for any cosmological applications. And going forward, this DM host term might end up being one of the dominant systematics in any precision cosmology applications for FRBs. So we should continue pushing in this direction of trying to understand what dominant FRB formation channels are. With that, I'd like to conclude by saying that from the discovery of the first FRB to the VLBI millisecond localizations of all FRBs at hand, we've come a long way. The host galaxy stellar population studies have helped us establish the fact that there could be a support for multiple formation channels, including young formation channels in dwarfs and spirals, to old stellar populations in globular clusters or even elliptical galaxies. There's increasing evidence that we need high resolution imaging as well as spatially resolved spectroscopy to really put constraints on the progenitor age and look for preference for high star formation efficiencies in the galaxies. And all of this is also important for doing precision cosmology because we need constraints on host galaxy systematics in such analysis. With that, I'd like to thank you all and take any questions.
Am I not?
Yeah.
So could you go back to the slide where you said that passive, FRB is very passive direction.
This one?
Yeah. May I know how much number, how much parts did you get this from? What are the numbers?
So this is the sample of, I think, 54 FRBs. And we are mostly working in low redshift bin, which is like redshifts up to 0.2. So if you cut the sample further down, then it's a sample of about 20 FRBs up to redshift of 0.2. And that's primarily the reason why your Poisson uncertainties here are also huge.
Because if we can increase the number of samples, let's say by a factor of 1 or 2, change, could conclusion change?
It really depends on whether or not we're able to fill in this low mass gap. I guess if you look at recent time localizations for low DM events, most of them seem to be associated with massive galaxies as well. But it's not very clear whether or not that could be an observational bias because your localization uncertainty is huge, so you are really preferring those massive galaxies. So I think with, let's say, chime outrigger, ASCAP, and DAC pushing in directions of larger sample, we should be able to better understand whether or not this gap could be real or not.
Okay.
Yeah, thanks for your question.
Further questions?
Hello. Yep. In the 7 or 8 slide, you showed the the magnetar is associated with nebula based while backtracing the magnetars. Yeah. So here you have backtraced magnetar based on its transverse velocity. But what about the radial velocity? Because it can be in foreground or in background also.
Yeah, you're absolutely right in pointing out. And I think in most of such studies, that's like one of the dominant systematic that you can only be measuring proper motions in transverse direction. But I'm not sure if the authors in the paper really comment on the radial velocity being dominant systematic for at least this analysis.
Yeah, then it can be in foreground or in background also.
Any more questions?
Hello, thank you for that, such a good talk. So I wanted to know, do you also look for DM measure of host? Okay, so what's the error usually in the DM measure of host?
So there are multiple ways of doing that. So if you really want to do it from the angle of using the actual host galaxy information to measure the host dispersion measures, then one of the methods could be to look at doublets like O2 or S2 to put constraints on the relative emissions in the two lines, which is controlled by electron density. So that allows you to put direct constraints on electron densities. But then, of course, one of the other uncertain quantities is the length scale over which your DM is being accrued, which is unknown. So uncertainties from such methods could actually end up being very large. Other methods include like the DMZ analysis, where you fit for the host DM contribution as a systematic. And the typical variance in host DMs from there has been estimated to be about 100 to 120 parsecs per cc.
In your line of sight, so usually there may be also sometimes some other intervening halos.
Yeah, right.
So like in those cases, like how much does how much is the error in the DM measure?
So I guess Sunil is a better person to comment on the same because they do foreground mapping and actually like partitioning of DMs into foreground halos versus IgM. But I think my understanding is that host DM contribution is not like a dominant systematic there as well, because if your FRB is at high enough redshift, then the host DM goes as inverse of 1 plus Z. So that contribution is actually going down as well.
But like mostly you measured with spectroscopy, right? When there is a halo, there is also another ionized medium. So it would affect.
So I mean, again, it depends on the specific sightline that you're talking about. Let's say there's a sightline which intersects a giant galaxy cluster along the line of sight, and that contributes like thousands of DM units to your dispersion measure. Then the host DM of like order 100 parsecs per cc ends up being a very small contribution. So it's like all about relative contribution and how significant the host component could be compared to the CGM of halos.
So like how much is that error? Like what are we talking about?
I think it's order 100 parsecs per cc for host variance.
100 parsec, like that's a huge number. Okay.
But that variance is in rest frame, I must say. So if your FRB is at redshift of 2, then it would go down by a factor of 2 already.
Okay, and like how much does it change with the redshift, this error? Like
it goes as 1 plus Z. So you convert from rest frame to observer frame. Yeah.
So like at which redshifts, like can you you have measured the dispersion measure of the host itself? Like what's the maximum redshift?
So if you want to assume that your observed DM is largely just from host and its CGM, then you probably need to stay in the local universe, like up to, let's say, a couple of tens of or hundreds of megaparsecs. So this is like Calvin's work recently, where they claim that most of the nearby FRBs have their DMs coming from CGM of the host itself. So you can put constraints on DM of the host component. So that's one method of doing it, like looking only at the nearby FRBs.
Like I wanted to know the number, like around what redshift or what megaparsec, like are you using? Like less than 0.05. Okay, thank you.